Hi, my name is Charlie Vorbach, and my final project used the differential flatness property of quadrotors to stabilize trajectories. Here you can see the final result with the quadrotor's trajectory in green converging to the desired trajectory in red. We'll look at how we got here, starting with the equations of motion that I used. They're derived from the Euler equations of motion, with the acceleration of the center of mass dependent on gravitational acceleration, as well as a thrust aligned with the body's z-axis, shown here in blue. Uh, the axis is the rotation matrix of the quadrotor, which describes its orientation, times a z unit axis vector, 0, 0, 1. F is the scalar value of the thrust. Additionally, we have the angular acceleration, which is a Coriolis effect term, plus a three-dimensional moment about the center of mass. These are our control variables. To integrate these equations of motion, I perform Euler integration, which is simpler than higher order methods, but sufficiently accurate for my purposes. I use quaternions and the quaternion exponential map because they can be very easily normalized by dividing by their magnitude. This helps prevent lots of numerical issues that I encountered while trying to integrate rotation matrices and then trying to use the Rodriguez rotation formula and employing other methods. The value of the exponential map can be found using this expression here, which is derived from the summation form of the exponential function and is closely related to the polar form of complex exponentials. Finally, I use spline trajectories because they can be very easily differentiated using this expression for their value at time t. This just lets interpolate between points from sampled from another trajectory. The control law is taken from a paper on geometric control of quadrotors and consists of a term that corrects the position error of the quadrotor, the velocity error of the quadrotor, compensates for gravitational acceleration, and compensates for acceleration of the trajectory itself. This whole sum is dotted with the body's z-axis to get a scalar value. Then the moment is found using a term that corrects for the error in attitude or orientation of the quadrotor, a term which corrects for its angular velocity, a term which compensates for the Coriolis effect, and a term which compensates for the acceleration, the angular acceleration of the trajectory itself. Again, complicated because we have to compensate for the Coriolis effect. These errors are carefully chosen so that I can prove exponential stability using Lyapunov functions over almost the entire state space. I show this proof in my report. With this control law, I can execute very dynamic trajectories, shown here with the red loop, and converge to the correct trajectory even with extreme errors. Here I show the drone is perpendicular to the ground. It has an extreme error in pitch angle, but is still able to converge to the desired trajectory by executing this very dynamic maneuver, which involves both a backflip, which you'll see in a moment, and a loop-de-loop in order to slow down. There's the backflip, and here's the loop-de-loop. It converges almost exactly to the desired trajectory. I also examine the effects of random noise on the controller. Here is noise drawn from a Gaussian zero mean distribution. Even with relatively large standard deviations, it can more or less follow the desired trajectory. More serious is constant perturbation, which shown here is a constant perturbation of 1 Newton. You'll see that the quad rotor fails to follow the trajectory. It becomes unstable in the presence of constant noise. This is problematic because constant noise is very common in real life. Things like wind cause it. So future work would focus on finding a way to eliminate this sort of constant error while maintaining stability, as well as evaluating the performance of the controller in real life. That would require dealing with things like sensor noise and imperfect state information, and could potentially be solved by using this controller as an initial guess for a trajectory optimization or model predictive controller. Finally, tuning the weights for faster convergence could definitely help it follow the trajectory more exactly and more quickly. Thank you for listening. I had a lot of fun with this project and hope I've shared a little bit of it with you.